Um, Today we'll be finishing the last two subsections of Chapter 9, the titration. And before we go further, I want just to share with you that we have the last, I don't know if it will be the last, maybe when we come back from the Thanksgiving holidays, we might have another last extra credit. Now we have extra credit here coming December 2nd when we come back from the holidays, from Thanksgiving holidays. So this is about donating like, acid-based donation. So you are donating your blood and people will be thankful. The Red Cross van will not come here unless they have 35 students. So they put a restriction here. They have to have 35 students. It's very expensive to operate those big vans with all the equipment inside and all the stuff inside. Very expensive. So the Red Cross is a non-profit organization. So they need 35 students. So I will, if you are interested in improving your final exam grade and by taking advantage, and you donate, that's a good stuff. I donated blood through all my life, so you do good for other people. So you have to register yourself here, and you have to schedule your blood donation appointment today. So you call them that you are from Clarkston Campus, and they are already know that they will be in December between 9 and 3 p.m. You take a video of yourself being, donating, and then you post it in the assignment section. There is a section for it. So if we don't have 35, that's what we were told, students, they will not come. They have to have enough blood, to justify the cost of operating this van. Did you see the Red Cross van, the big one? It has all the equipment and all the staff there, and everything costs money. Although they are non-profit organization, but still cost money. And if they have 35, that's what the limit they put. They will be very thankful. Last year, I put an announcement. Guess what? Over 70 students came in for my all sections. I have 5 sections, 5 classes, different higher chemistry, lower chemistry labs. And they came and they told them we have to come again. They came twice for the people who just took 35 and then they have to come up and then take the rest of the 35. So about 70 students. So if you are interested in doing something good for yourself and for the others, you can call 1-800-RED Cross. Just match those alphabets with the numbers. Call them and tell them that you are from Clarkston Campus, Georgia State University. They know the appointment and they're waiting for 35. If they don't get 35, we have to cancel the extra credit. However, I put the extra credit there in the box, drop box, so you can still write an essay, one page summary about donating blood. Okay. This is for the extra credit. Yesterday we had another extra credit, as you can see from the videos here. Those are international games, different games, or Korean games, Japanese, American games, all over South American games, and all those games are there. So we have this blood drive, and then when we come back, there might be another last one. So we are interested in finishing up the buffer. So let's talk about the buffer. Somebody will tell me what we mean in English. What's buffer means in English, just as a word. So if you hear something about buffer, what it comes to your mind? What's that? No, be concrete, a little bit, very specific. If I say between South Korea and North Korea, there is a buffer zone, military buffer zone. Meaning, yeah, you said the answer, but with the sign language. No, I need talking, not sign language. I need to talk. You heard it. Well, a buffer zone, a military buffer zone between South Korea and North Korea. This is a zone by which uh, no military from South come to the North and North come to the South. Is a neutral, yes, it's a neutral zone. A neutral what? Zone. Nobody will intervene in it. So there is a neutral zone between the two countries. And it's the same thing here, definition in chemistry. When I say this, I have a buffer solution. This buffer solution is, let's write it here. A buffer is a solution that always we add it to resist any change of a pH, make the pH unchangeable. If it changes, it will change small, tiny amount, not that much. So a solution resists the solution that resists any change in the pH, correct? And we define the pH, just a reminder here, this is actually is P, HO3 plus will be minus log the concentration of H3O plus. We said the proton is not really existent. We have hydronium ion, H3O plus, correct? So this is one of the best example for us is a human blood or insect blood or whatever human blood. Human blood is a buffer. I think I'm not sure, but the pH operates at pH around neutral, 7.4 or 7.2, something like that, between 7.4 7.2. So it's neutral, correct? And this is very important. Now, if somebody will swallow some poisons, somebody wants to commit suicide, or somebody wants to kill somebody else, and that somebody else is put inside the coffee or a drink some poison, and somebody took this poison in, the poison, then what will happen, most of the poisons, they are acidic or what? Or basic. Some of them neutral too. But a lot of poisons are acidic or basic, correct? And that's what they have drastic effect on the blood pH. So then if you have too much of this poison, that will have, the effect of the buffer will be what? The effect of the buffer will be destroyed, and that person will die because the pH is changing. Any change of this unit here, any change, a small tiny change will cause death. Any small change will cause death because the pH of the blood has to be kept neutral, very close to neutral, or I will say neutral. Now, if you add poison, if you take a poison that's acidic, too much of it, that will destroy the buffer of function of the blood, and then your blood will be acidic, and that will cause internal poisoning and cause to death. So any change in the pH of the blood, whether it's acidic or basic, causes a death of that person. Okay, guys? And that's what really the buffer is. It's the same like in the language. Buffer means you are neutralizing things. You don't need any change. So no change in the military situation between North and South Korea. Through this zone, we can preventing any intervention or any war between the two countries. So that's the same idea in chemistry of buffer. So now, second thing to know, how we can make buffer inside the lab. It turns out to be, can I have this one here? Everybody has it? Everybody has it? Okay, so stick this one out here, and then let's look. A buffer is made of two things. A buffer is made of weak acid, and this is very important, weak acid plus its conjugate base. Okay, such as, I can switch this one here, guys. CH3, weak acid. This is acetic acid, the vinegar, correct? Acetic acid. And we did this one here in the titration. As we said, that's our vinegar. And conjugated base is sodium acetate. Sodium is a spectator ion. Sodium here, spectator ion, has nothing to do with the reaction. Spectator ion. But then the acetate here is the conjugated base. Okay, so that's a buffer. You have an acid and its conjugated base, or we can have the or weak base plus its conjugate acid. Okay, an example of this, we'll have an example of this here. Ammonia, that's a weak base, and conjugated base is ammonium. So this is conjugate acid. Okay, so you can make this one here is made of, you can make it out of weak acid with its conjugated base, or a weak base with its conjugate acid. So those are the ones. Now, we had here in the, let me just, everybody has this first, everybody has this before I delete it, everybody has this? Everybody has it? Okay, so let's take this one out and look at the, those are examples of buffer. So those are the examples of buffer. Okay, so those are the examples of the buffer. So we have, this is ammonia, it's a weak base, plus ammonium conjugate acid. This one here, HCO3, correct? Minus, oops, sorry. Minus, that's a weak base, plus CO3, 2 minus, correct? This is, no, HCO3 not a weak base because it has a proton, I'm sorry. It has a proton, so this one here will be, it has this one here. That's weak acid. It has a proton. And the carbonate is a conjugated or conjugate base. Acetic acid, the same thing here. CH3COOH. This is a weak acid. Plus the acetate here is weak, not weak, conjugate base. And here, as you can see, it has an acid, phosphoric acid. It's a weak acid. And H2PO4 1 minus is a conjugate base. So now we have all this system here. So those are buffers. Those are well-known buffer. We use them in the lab for different pH. So they create different pH, correct? And the last week we did an experiment together with the pH being 3. We used the pH buffer solution, the pH 3, and the buffer solution with the pH 9. So two buffers here. Okay, guys. Now, how we can calculate the pH of a buffer? You are not will be not asked in the exam or in my quiz, or in my quiz. I'm not sure, but in my quiz you might be asked, because it's an open book and you have the formula here for you. I wrote for you the formula here. Where is the formula? So let me first ask if this is. Are we done with this, guys? Are we done? Everybody has it? Everybody has it? Yes? Okay, let's take this one out. And let's put this one here. And then let's have this one here. I want you just to write this one here. I'll wait for you to write this one here. But I'll make it smaller so you can. This is Henderson-Hasselbalch equation. Henderson-Hasselbalch equation that we can use to determine the pH. Here it is, equation. This is an equation. Here it is, guys. Used to determine what? The pH of a buffer. The pH of a buffer. So this is molarity or concentration of conjugated or conjugate base, correct? And this is molarity or concentration of weak acid. This is minus log Ka. Ka is acid dissociation constant, and always is given. Always is given from the literature. Okay, guys. So we have everything. Let's look. I want you to have this one here. Take maybe snapshot of it or make a picture of it with your phone so you have it. This will not come in the exam. As a matter of fact, this is a higher general chemistry one. But at least I'm not scaring you or something, but at least you get the feeling how we can determine that the pH of this buffer is 3. The pH we worked in the lab is 9. How we determine this? Well, we mix the salt with what? With the acid. So, for example, okay, guys. So, I'll give you one example. Everybody has this one here. Everybody have taken a picture of this. Okay, so I have here, just to let you know here, I'll give you all the information. I have here, take the blue color here now, changing, they said the color of the marker will keep the students awake, not sleep on their instructor. So I'm changing the colors, blue now. The weak acid, will take the weak acid, okay, is concentration of it is acetic acid, vinegar, correct? We'll do something closer to whatever we have, the sodium hydroxide. Somebody remembers from the lab what was the sodium hydroxide concentration? Close 0.1 something, correct? 0.1 something. Somebody remembers? 0.1, say 0.1 whatever. So say 856 molar. That's acetic acid. That's vinegar. Okay. Then its conjugated base. This. Its conjugate base, which is sodium acetate. We said this one here is a spectator and has nothing to do. This is the conjugate base. This is here and plus spectator ion. And we'll say this one here, the concentration of this is this one here. Just hold on. Okay, guys, the concentration will make them equal, so that will be very nice to cancel. 0.1856 molar. Okay, guys, the Ka of acetic acid, Ka, dissociation constant of acetic acid is 1.8 1.8 10 minus 5. So question is, with the red here or with the say blue, what is the pH? What is the pH of this buffer solution? So what I'm going to do here, just plug in the numbers. This number here, the concentration is 0.1856, and this is 0.1856. Those are canceling themselves out, correct? That will be what? Log of 1. Log of 1 is what? Somebody will tell me. Log of 1 is what? 0. Yeah, somebody got, thank you very much. Somebody is still awake here. So log of 1 is 0. So this, now I made it on purpose. That's what we do in the lab. We keep the concentration. We weigh this one here, solid, dissolve it in distilled H2O. So the concentration will read, we need this one here. We can calculate how many grams of this to make it this molarity. So we'll prepare this one here. We'll prepare this by dilution as well. Keep them the same so they cancel. So this is, the whole thing is 0. Now, how about minus log 1.8 minus 5? So this is pH is, now the pH is equal to what? Minus log 1.8 10 to minus 5. Well, let's do it here with my Microsoft Windows 10 or Windows 11, I'm not sure. But I think Windows 10, we're still Windows 10. The university is not adopting very rush any new Windows. They keep it for testing for a long time. So we are still on 10. So what this Windows here, scientific That's for free. You don't have to buy online calculator. This is inside the window. Snipping tool, long time ago, about 20 something years. I told you I bought it about $45. How much? $45. And scientific calculator, you can buy that from Amazon online. So that's the same amount. Those are virtual one, not a real one. So now what I will do here, I'll put this one here, 1.8. Each calculator, whether it's online or physical calculator, will have different way of manipulation, different way of operation. So if you have HP or TI, Texas Instrument or the other HP, so they will give you, you have to start with log. But here you cannot start with log. It will give you an infinite number. This is an error. So you have to put the number 1.8 and then exponential. In the TI and the HP, you have exponential E with the alphabet E. Now some TI and some HP, they put double E, means exponential, the same thing. So you have to, I learned from this scientific online, Microsoft Windows 10 and the Windows 11 will be the same thing, is EXP, that's exponential. So, and then I have minus this plus, so I have to add minus in front, it's small tiny minus plus, and then 5. And then that's the value. First I put the value, then I click on log. See here? Give me the value. So the log is, how much is it? Came out to be this number. So I will just copy this number somewhere, put it somewhere here, and paste it. So it is. So it's 4.744. Now, how many, question to you, how many digits should I have here? How many digits should I have here? I mean, my answer is, my answer. So the molarity is 0.1856. The log is 1.8 10 to minus 5. What will be my answer is? Somebody will tell me. 5. What do you think? Guys, this one here, this value here, plus what? Plus 0, correct? So the 0 is gone. I don't have any digits, correct? I have no decimal. That's 0. So it's really, it's about this value here. This value has how many significant figure? 2. So how many digits I will have? How many digits I will have? 2. So then I will have 4.74. This is minus, because the minus with minus, the minus with the minus here will cancel out. So the pH of the solution is 2 digits after the decimal, because I'm considering this value, not this one is gone already. This one is gone. It's not part of the consideration, it's gone. Correct? So I consider whatever I'm doing the calculation with. So the pH is 4.74. I have 2 digits here. I have 2 sig figs. It is 2 sig figs. And therefore they have 2 digits after the decimal. Okay, guys? Let's look at the PowerPoint. You have an example there different from what I have, but we'll look into it together. So first I'll give you some time to have this. Everybody has it? Everybody has this? If you can't catch up, you can take just a snapshot of it with your phone, and then you can upload these pictures in your iPad or desktop or laptop. So I'll take this one out, and I'll take this one here out as well. So let me here get this one here, and then let's go to the here is the effect. How does it work? I'll show you this, but I want to show you how to calculate this. Now this one here, if you look at this example here, guys, Look at this example here. I have, this is the Anderson-Hasselbalch equation, correct? This is the conjugate base. This is an acid, weak acid, correct? And the Ka is 6.10 minus 4, correct? The concentration are not the same. The acid is 0.25, so you'll put at the bottom is 0.25. The conjugate, this is an acid value, the concentration of the acid. The concentration of the conjugate base, which is sodium, is what we said, that's spectator ion, so don't worry about it. Spec ion. Spectator ion, correct? So don't worry about it. So, but it is the fluoride minus is the what conjugate base, correct? And it has a concentration of this. This is a conjugate base, correct? This is HF. This is F minus. When you prepare them, correct? So this is 0.1. You take 0.1 molar divided by 0.25 molar. Take the log of this, and the log of this came out to be minus, correct? And then the log of the Ka for hydrofluoric acid, Ka for hydrofluoric acid is given to you is 6.8 10 minus 4. That's for HF, hydrofluoric acid, So you plug everything in, and you'll end up with the value looking like this. The question is, correct? You have all those are two significant figure, and you are taking this two significant figures, so you'll have 2 digits after the decimal. You stop here, so you stop on this. This is 9 will come out. This is 9 will come out as 1. So the answer is 2.770. The answer is the pH of this solution is 2.770. Okay, guys. Now, how does this buffer is functioning? How does it work? Okay, so let's wait here a little bit. Everybody has this. Everybody has this. Everybody has it. Okay. So let's take this one out and look how the whole thing is working here. So I'm taking. So if I have acetic acid, for example, if I have acetic acid, correct? This is my buffer, correct? It's acetic acid. And dissociate in H2O to give me H plus, H2O here, H3O plus, plus CH3COO minus. This is a conjugate base. This is weak acid. So we are looking at this, and we are looking at so now what will happen, this is the buffer, Now if I add acid to it, addition of extra acid from outside, externally, not internally, that's external. So I will add acid to it. You add extra acid means you add is added. More is added from outside. From outside. Correct? So this is equilibrium, goes for back and forth. So if you add an acid, what will happen here? If you add an acid here, what will happen to this? The shift. Where will be the shift? Somebody will tell me where will be the shift? This is an equilibrium, correct? Now you add acid to it. Shift will be where? Acid will add itself where? To the left or to the right? Where is it found? Found in the left, correct? Shift will be where? When you add acid, shift will be where? To what? To the left. Shift to be to the left, because the acid will add itself to the acid. So what it means this? It means meaning. The amount of this will be less because it has to react with this to go to breathe. So meaning the acetic acid at left concentration will be increased slightly. And this one here, this is at the left. And the acetate at the right will be decreased slightly. Okay, guys, that's what it means. So if I add an acid, the shift will be where? To the left. Everybody's following? So this is a very small amount, not that much, because this buffer is to resist any change on the pH. So now if you add the base, now the base will come and scavenge the protonium ion out to produce H2O, and then the shift will be to the right. But let me just go for this one. Everybody has this? I will add a base now. Everybody has this? Everybody has it? You can take a picture out of it, so if you want to. Okay, everybody has it? Okay, so let me take it out. I'm not taking this one out, but I will be using those. Addition extra, not extra acid, but addition a base. So okay, so then I have to see where the shift will be. Just take those out. Okay, guys. Now, if I add sodium hydroxide to this, add externally out a base. So I'm adding addition of a base, such as sodium hydroxide. So the sodium hydroxide here will come and react the OH from sodium oxide. Sodium is, again, this is spec ion, spectator ion, spectator ion, correct? But the OH here will come and scavenge the H3O plus to produce H2O. So when you add this one here, this one will be scavenged by the OH, correct? Will be scavenged by the OH. So if you look at this, will be scavenged by the OH. This is 2 here. So therefore, this arm of this right of the balance will be less because you are scavenging this one out, this one here. So here it is, the conclusion OH removes H3O plus from the equilibrium, So then if that's the case, you are removing it from there, then you have shift will be which way? Shift will be to the right now, because acetic acid has to react to compensate for the loss of the hydronium ion. Shift will be to the right, meaning the acetic acid concentration will be slightly decreased, and that's the shift. So meaning that's the acetic acid, and the acetate here concentration will be slightly increased. So always decrease, increase, and small amount, the pH will not change that much, So they will say that the buffer is kept, keeping the solution from being changed in its pH. Okay, guys? So let's go and look at your PowerPoint and see what they have. Can I take this one out? Everybody has it? Everybody has it? Everybody has it? Okay, guys. Taking this one here, and here it is. Here now you can see that you have a system. It's a basic system, basic buffer, correct? And this buffer is made of a base. This is weak base, correct? This is weak base, ammonia. And this one here is conjugate acid of this base, correct? So this one here, and if you add an acid, the acid will come and scavenge what? This one out. You have an acid like this one here. I'm talking about this one here. So if you add an acid, then the acid will come and scavenge this one out. This one will be removed. The shift will be which way? This one will be removed, correct? So the shift will be which way? To the right. Shift will be to the right, correct? Well, it's the shift to the right, meaning what? Meaning, when I say shift to the right, meaning this concentration will go a little bit slightly down. This concentration will go up. Now, if you add a base, such as in case of this one here, if you have OH, then you will see the OH is, you add OH from outside, the OH will add itself with the OH here. And the shift will be, to the left. Shift. Correct? Shift will be because you added extra OH, the OH is present at the right. So this arm, the right arm is, overstressed. Shift will be to the left. What it means that the ammonia shifting to the left, ammonia concentration will go up, and the conjugate base will go down. Okay, guys, that's what we have discussed. But the increase and decrease is so tiny that will not have any effect on the pH. Okay, guys, this will cover the pH. This will cover the pH. But the main thing is to know the multiple choices. I'll just go back and look at what the exam they might bring. So can I take this one out? Everybody has it? Everybody has it? Okay, now if I look at this, that's what the question here. They'll bring you some things here, and they'll tell you determine if this is a buffer or it's not a buffer. We can look at the some of the worksheets and see. You tell me which one of those is a buffer. I'll try to bring you something from my head. Um, let me hear. Okay, guys. I have I have. Okay, guys. Which one of those is a buffer? Which one is not a buffer? So I'll give you another one. Another one. Another one. I'll give you another one. So now you tell me. I'll just make yes or no. I mean, the first one, chloric acid and perchloric acid. This is perchloric acid, and perchlorate. This is a buffer or not a buffer? Come on, guys, don't let me down. It's a buffer. It's a buffer. How many of you say? How many of you will say this is a buffer? 2, 3. Okay. How about the rest? Any reasoning? The answer is no. Cool yourself down. Cool yourself down. Why is no? Because perchloric acid is strong acid. You have to have what? Perchloric acid is strong acid. You have to have what? Weak acid or weak base. Strong acid. And the buffer will never allow any strong acid. You cannot have strong acid. You have to have what? Weak acid. So the first one is not a buffer. How about the second one? H2S. What do we call H2S? What's the name of this gas? I know it's dihydrogen sulfide, but what's the funniest name of it? It has a very funny name. This is called farting gas, smelling very bad, coming out the gas from the body of a human or insect or animal or anything. You have to have some very bad smell. Like the skunk, the skunk animal? That's even worse than H2S. It has markup tail, which is really part of it, H2S. That's a very bad smelling gas coming out. It's part of the digestion processes inside the stomach. So part of the digestion inside the stomach will create this H2S, and especially if you have digested some food that has, it's not matching with the HCl or whatever, so you get some food will create a lot of H2S. So that's a farting gas. Smells bad. It's like skunk has a markup tail, even worse than H2S. Part of it H2S too. So it is a buffer or not a buffer. Those type of questions they will come in ACS exam, the lecture, and might be in the lab. So which one is buffer? Why? H2S a weak acid. This is correct. That's a weak acid. Weak acid. Yes. This one is no. How about HCl and Cl minus? Is a buffer or no buffer? Come on, guys. Come on, guys. No. No. Somebody said no. And that is correct. Why? This is strong acid. This is strong acid. We don't need strong acid. We need weak acid. That's a no. How about dihydrogen phosphate and hydrogen or monohydrogen phosphate? This is an acid. This is conjugate base. So, is this a buffer system or not? A buffer or not? This is yes. Why? Because phosphoric acid and dihydrogen phosphate ion are a weaker acid. Weak. As long as a weak acid is yes. That's a weak acid. How about nitric acid and nitrate? There's nitrate here. Oh, sorry. Nitrate. So, is this a buffer or not a buffer? Come on, guys. Nitric acid, nitrate. Is a buffer? Yes or no? Yes or no? Answer is no. Why? Nitric acid is strong acid. We are not strong acid. Strong acid is not making or preparing a buffer. How about hydrogen sulfate and sulfate? H2SO4, 1 minus, and SO4, 2 minus. It's a buffer? Yes, because this one here is a weaker acid. Weak acid. Okay, guys, that's the way it will come in the SS exam in the lecture. I might appear inside the final exam in the lab. I don't know about the lab, but it's a possibility. But in the lecture, yes, that will bring you something like this for sure. So, any question about this? We'll go for the next topic. The last topic is salt hydrolysis. Can I take this one out? Okay, let's take this one out. And the last topic is salt hydrolysis. So we'll have salt hydrolysis. So what do you mean by hydrolysis? Well, hydrolysis is a dissociation of a salt in H2O to produce weak acid or weak base. Okay, you have to produce weak acid or weak base. That's when you take the salt and dissolve it in H2O, you produce weak acid or weak base. Okay, guys, and we can determine this with the hydrolysis. One can determine if the acid is acidic, not the acid, is the salt, sorry. If the salt is acidic basic, or neutral. Okay, let's put some examples here. Let's put some examples. Okay, guys, everybody has this? Take your time, everybody has it? Everybody has it? Okay, I'm taking this one out, and then I put, we have to determine whether those acids here, maybe I'll just, I'm copying one at a time. We'll make one at a time. So let's go here, and I'm pasting those here. Okay, guys, we'll start with acetic acid. So this is called potassium acetate. Potassium acetate. Okay, so we don't know it's acidic, basic, or what, or neutral. Well, we take the way we can approach it. We are approaching this. We take the potassium acetate, add to it HOH. I'm writing HOH. This is H2O. Is another way to write H2H. So then I will say this one is, I will make it even. It is H plus OH minus. So this one here is H2O. Okay. So now this one will be dissolved, will give us in H2O, will give us CH3 minus and potassium positive, correct? Now, since this one here is positive, we react with the negative one. So with H2O, H plus OH minus, that will give us, the H will come react with this one here, will give us CH3 COOH plus, then the OH here, the potassium is spectator ion, correct? So this one here will react with this potassium, not spectator ion, but we can let it react with H2O plus H plus OH minus. So this one here, this one will not react. H plus will react as to make acetic acid. This one here is the potassium, then will react, will give us, this is positive, this is negative. We'll have KOH plus H plus. This is will give us acetic acid plus OH minus. So the OH will not react, the OH will come here. This one here will come here, this one does not react, will come here. So this is the reaction of the hydrolysis of the salt. How does it work when it's reacted with H2O? The acetate will come and react with H plus to give you acetic acid, and left over is this one here, will come here. The K plus will react with the OH minus, the leftover will come here. Now, which one is hydrolysis, which one is no hydrolysis? This one here is what? Strong or weak? This one strong, correct? This one here is strong base. Since we have strong base, we'll say okay. So this one here, no hydrolysis, no reaction. No hydrolysis. No hydrolysis, no reaction. How about here? This one here is a weak acid. Then we have what? We have here is here's no, here is yes. Yes, we have what? Here we have hydrolysis. Why? It's producing a weak acid or weak base. This one a weak acid. What's left over here? So this one is hydrolysis, this side. But what left over? OH minus is left over. So therefore, because OH minus is left over, so this potassium is basic. Why? OH minus is left, so this one is basic. Get the idea? You get the idea how we determine this basic? We dissolve them both, the cation and the anion. We add H2O to the anion, H2O to the cation. The cation is producing a strong base, and that's no hydrolysis, correct? So the anion acetate producing weak acid, acetic acid, and OH is left over. So the OH left over is basic. So CH3COOK is basic. So let's take NH4Cl. Let's take the second one. Can I take one out? Can I take one out? Take it out? Okay, so let's take the second one. So I'm taking the second one, which is, I'll make it like this, NH4Cl. Okay, so this one here plus H plus OH minus. I have H plus, this is 4, Cl minus. Then I will add to them plus H plus OH minus. And this is H plus OH minus. I add H2O to them, correct? And here we are. So the ammonium chloride will react with what? What do you think will be very close to this? This is positive. The positive has to react with the opposite sign. So this is negative. So the reaction will be between those two. So you get ammonium hydroxide plus leftover is, this is left over. This one here, this negative will not react. It will react with this one here will be HCl plus OH minus, and this is left over. Okay, guys, now, which side has hydrolysis? Which one has hydrolysis, guys? Which one? This one hydrolysis? No hydrolysis. Why? Why is no hydrolysis? No reaction. Why? Correct. HCl is a strong acid. Hydrolysis has to produce a weak acid or weak base. Here is a base, correct? Ammonium hydroxide. But it's a weak base, correct? Since it's weak base, then there is reaction. There is hydrolysis. And it is yes. And this is no. Correct, guys? Now, ask yourself, what is left over? What is left over? This is left over. H plus is left over. So This is acidic because now H plus is left over after hydrolysis. So this salt is acidic, correct? Correct? So let's take this, the third one. Let's take the third one. We're going to finish as much as we can, and you can do the rest of those. So can I take the other one? Okay, let's take sodium chloride. And then you can do the rest yourself. If you have any question, come and see me because we are almost there. So sodium chloride, see, sodium chloride plus H2O, I get sodium plus chloride in H2O. Then I will add H2O, H plus, or H minus to this. And then I will add H plus plus Cl minus, or H minus to the other one. So make a line here. So look at this reaction here. Here H positive, it will react with this, correct? So those are together positive, negative. So it will produce NaOH. Left over is plus H plus, correct? This one here, this one is negative. We react with the positive here. You get HCl plus OH minus leftover, correct? So now, this is strong acid. Strong acid. This one is strong what? Base. So, no reaction, and here no reaction, no hydrolysis, because both of them strong. Strong, strong, nothing there. So this salt is what will be neutral. You are measuring the pH of H2O neutral. pH of H2O is neutral. Correct, guys? So I think I'll stop here. This will conclude the whole chapter. You can try the other two salts, and if you have any question, come and see me. Thank you very much. And we'll meet in 1 week, after 1 week, after Thanksgiving week. So don't come next week. The university is closed. Thank you very much.